Hi everyone, Mr. Neighbor here, and today we're going to start chapter 12 with forces. The first section in chapter 12 is all about Newton's first and second laws. First, a little history. We talked about Aristotle, who was the philosopher and metaphysicist that analyzed motion purely on logic, and his belief was held for over 200 years, and people that disproved it were taught with Aristotle's ideas. They didn't believe those, though. So, one of the big things that Aristotle thought was that there was violent and natural motion. So, violent motion would be a ball being kicked, natural motion would be that ball coming to rest, rolling to a stop. He thought that the natural state of motion or a body was at rest. That's the natural state. Galileo, raised on Aristotle's beliefs, did not believe that logic should be the sole determining factor of how the universe is represented. He thought that there should be some tangible proof, that there should be some results that actually support that. And he disproved a lot of Aristotle's beliefs based on solely logic alone, using some of his own logic. And then Sir Isaac Newton, continued on with Galileo's study of motion, and he published one of the best known books on math and physics called The Philosophy and Natural Principles of Mathematics, if I'm translating that right, which summarized all of his studies, but he didn't write a whole lot besides this. It was written in Latin, which was the language of scholars, and a lot of people consider it to be the single most important scientific book ever published. And it included his analysis of motion and summarized his 3 laws of motion. So just to recap, these laws of motion will deal with force. So let's recap what force is. A push or a pull that happens on an object. That force doesn't always cause the object to move, but it does cause distortion. So think about a soccer ball. If you ever see a picture right when it's kicked, you'll see that soccer ball not perfectly round, but there'll be a little indentation where the foot actually is impacting the ball. You could think about a rope being pulled. That rope might have been thicker, and then when you pull it, it stretches out, so it's thinner. But there's a deformation, there's a change in shape somehow. Remember that forces have a magnitude and a direction because they are a vector quantity. One of the most common ways of measuring force is with a spring scale, which I have pictured right here. So a spring scale, you would hook something to it, and then that object would be pulled down or pull the spring in here, and then it would tell you how many newtons of force is being applied. And again, the units are kilograms times meters over second squared, which is a Newton. We will talk a lot about mass and weight, 2 different things. So let's define first what mass is. So it's one of the single most misunderstood concepts in chemistry and physics. It's not the same thing as weight. Those are 2 different measurements. Mass is a measure of the amount of inertia that a body has. It's a measure of how hard it is to change an object's motion, in other words. So the more mass you have, the more inertia you have. And the more inertia you have, the harder it is to get you moving if you're not already moving, or to stop your motion if you are moving. Thinking about a bus. That bus, if you go to push it when it's at rest, even if the bus is out of park, the e-brake's not on, it's going to be hard to push because it has a lot of mass, a lot of inertia. If that bus is moving down the highway, you're not going to run out in front of it to stop it because it has a lot of inertia. It's going to continue going in the direction it's going at that speed it's going at. You're not going to have a whole lot of effect because it has a lot of mass or inertia. So mass is measured by a balance where on one side of the balance we have a known quantity, and on the other side of the balance we have an unknown quantity, which you're trying to measure. The official units of mass are the kilogram, which is about 2.20 pounds, and a gram is 1,000th of a kilogram. And on Earth, is about the weight of a small paperclip, if you want a comparison. Over on the right here, we have one of the actual sets of the kilogram, which was, I think there was maybe 7 or 9 of them made at one time and then placed around the world. So we have a standard to go by. This is what a kilogram is. If we lost those, we wouldn't know what kilograms are. I mean, we have other things that we can measure with, but those things deteriorate. Those objects, those weights on the balance to measure mass, they will deteriorate. That's why we have all these glass containers over top of this little kilogram right here. So it preserves it. But even that's not preserving all these different kilograms. They were made at the same time and they had the same mass, but that mass has changed for all of them now. It was the same thing with the meter. There was a stick, a rod that was the meter, and there was multiple ones, and those multiple ones were different lengths after a number of years, even kept out of people's way where it couldn't be interacted with on a regular basis. So they are moving away, scientists are, from using physical representations of measurements to more conceptual things that won't change. So the meter is now a portion of a light year, the distance light travels in a single year, which is not going to change. So we don't need an object to represent it anymore. All right, so let's do some practice. A spring scale is used to measure forces, but can you measure the mass with a spring scale? Yes and no. Sometimes is the answer. So a spring scale measures force. Force, we will learn, is calculated with mass, so you can find it. But the problem is, if you ever go into outer space where you don't have the gravity of Earth as strong as it is at the surface, that spring scale isn't going to be pulled by the object. Everything's just going to float. So then you can't actually see the force, which you can't find the mass. So mass and weight are not the same because you have weight on Earth. You don't have weight in space. You have mass on Earth, but you still have mass in space. So we need another way to calculate mass more regularly. But for weight, weight is a measure of how strongly gravity's pull is on a mass. So it's a measurement of force. So we'll see it written as F sub G or sometimes with a big capital W. And because it's a force, the SI units are newtons for that. So weight is calculated by taking mass, whatever that is, times gravity or acceleration due to gravity, 10 meters per second squared, or 9.81 if you want to use that. All right, some practice. Here's a statement. I weigh 79 kilograms. Is this an acceptable statement? No, because it's talking about weight. 7 kilograms is not a weight, it's a mass. So it's not true, and it wouldn't be true in outer space either. Mass is the same everywhere. So I am 79 kilograms would be a true statement. I weigh 174 pounds. Is this an acceptable statement? Pounds is not typically thought of as a force. It's more of a mass thing. So that's, again, not a good statement to say. And then lastly, I weigh 774 newtons. That is an acceptable statement because weight is a force. Newtons is a force label. What is the relationship between a newton and a kilogram? 1 kilogram is that many newtons. We talked a bit about inertia already, but it's another name for mass. And the more massive something is, the more inertia it has, the more resistant to changing its motion it is. So think about a sumo wrestler. They have a lot of mass, so it's very, very hard for them to be moved or to change their motion or to get them off balance. More mass, harder to move, more inertia. Also, if something is moving, it's harder to stop that motion if it has a lot of inertia. So just think of inertia as more massive, harder to stop, or harder to get going.